Welcome to the NMR physics class. Today we're going to talk about some basic pulse sequences for NMR spectroscopy. I am Graham Mason. We've talked before in general terms about the need to create a net magnetization, and we do that with by putting our sample in a strong magnetic field. We get a small and slight majority of the spins are aligned with the magnetic field, and that's what we call the net magnetization. We detect that by rotating the net magnetization into the XY plane using a radio frequency magnetic field called B1. And here on the right, you see the net magnetization vector is in the XY plane. And as long as that persists, we can detect the magnetization precessing there. But where is the signal in the sample? Where are the chemicals if we're going to study the brain? There actually is whole brain NMR spectroscopy done but it's only on rare occasions that it's used. It's simple to implement, but you don't know where in the brain or the head the signal is coming from. We also have a challenge of water if we are doing proton hydrogen, that is, magnetic resonance spectroscopy. Much of NMR spectroscopy, most of it, what is done in the brain, is done with hydrogen. Water has 55 millimolar concentration because it's H2O, that's 2 protons, 2 hydrogen atoms per water molecule. So it's 110,000 millimolar protons in water. Creatine, by comparison, one of the easier chemicals to see in the proton spectrum, has about 27 millimolar protons. How can we measure the metabolites in the presence of so much water? We have to suppress the water. So there are two challenges. We have the localization, and we have the water suppression to deal with. We'll start with localization. And one of the earliest localization methods, and very effective, it's still in use today, is ISIS. Image selected in vivo spectroscopy. And it's based on the use of frequency selective inversions. So in another class in this course, we talk about shaped pulses and frequency selective pulses. And some of those can do frequency selective inversions. That means they will flip the magnetization 180 degrees, but only over a specific frequency band. Block pulse has very low frequency selective, very poor frequency selection. It covers a very broad band of frequencies. And there are times when that is good, but it will not let us do ISIS. A sync pulse is very good at selecting a narrow band of frequencies, a very sharply defined band of frequencies, but not for a high tip angle. If we want to tip 180 degrees, we need something else. And one option, that's one of the first options that was used, is a hyperbolic secant pulse. It's called that because of the shape. It also has this property, it's adiabatic. An adiabatic pulse has the ability to rotate the magnetization, and when there's enough B1 intensity present, it will rotate the magnetization to where you want to put it, and then not disturb it further. So you can actually achieve a specific tip over a wide range of B1 amplitudes. And that is useful when the B1 amplitude can be different in one part of the sample or another. That is when a radio frequency coil applies a spatially inhomogeneous B1 field. These hyperbolic secant pulses can be very useful to use frequency selective inversions when there's inhomogeneous B1. Here are some examples of how you might use a frequency selective pulse. You might, for example, invert a water, a water band, a band around water, and wait some period of time before you begin your spin echo or your pulse acquire experiment, so that this water can go through T1 recovery and reach zero amplitude, zero zero Z magnetization. So that's one use. And so that because the chemicals are defined across a frequency band. Well, if you put on a gradient, now space is defined across this frequency band. And so you can, if you apply a gradient like you would for imaging, and you then apply a frequency selective inversion, you can invert just a particular region in the sample. So this could be used then for ICES, for volume selection. The simplest is one-dimensional ICES. It requires two acquisitions. In one of the acquisitions, you just carry out your pulse sequence, regardless of your regardless of any need to isolate a particular region. This might be a pulse acquire experiment, and you get a signal from the whole brain, or the entire sensitive volume of the coil. Then you do another acquisition, where you've applied a gradient and a frequency selective pulse to invert a region of the spins. If you subtract these two, then you'll be left with a signal coming just from the volume of interest. And that's because, see here, when you acquire a signal without any localization, we'll say there's an amplitude of 1. When you invert a region of the spins, and then you do your experiment, now wherever you didn't invert, it also has an amplitude of 1. But where you did invert, it has an amplitude of -1. When you subtract them, the 1 and the 1, everywhere there's a 1 in both cases, it disappears, it cancels. And you're left here with twice the signal from that volume. So there's not a boost in signal. It's twice the signal because you've done two acquisitions. The advantage is that where you don't want to see anything, you have no signal. These hyperbolic secant pulses have very sharp cutoffs on their thresholds for inversion. So you don't get a lot of fuzzy edges on your voxel of interest. Now, if you just do one dimension, you're selecting, effectively, you're selecting a slab. So if you were to do this experiment, you would select a slice through the brain, and you would isolate your signal to a slice. Usually, we want more isolation than that. And one next possibility is two-dimensional ICES. That will select, it takes the slice and then chops a section out of that. So now, instead of a slice, we have a column. And there is, so now that requires 4 inversion pulses. That requires 4 different acquisitions. One of them has no localization applied. Another, we have an X inversion. Another, we have a Y inversion. And another, we apply inversion pulses along the X and Y directions. And when those are combined appropriately, you select you use a cross section of a cylinder. This is used occasionally. What's more common is to do 3-dimensional ICES. That requires 8 acquisitions, various combinations, inversion of everything, inversion of all the double permutations, inversion of each direction, and then, as before, 1 acquisition with no inversion pulses applied. When you do these, you can get a block. You can get a rectangular block selected very precisely. Now, note that because it requires 8 acquisitions, the person needs to be holding still for at least 8 acquisitions. So it is more vulnerable to motion than the other localization methods that can be done in a single shot. But if you can coach your subject, the subject is cooperative enough, and you're studying an organ like the brain, which does not move very much, this can be very effective because of the localization is so sharp. And here's an example with some good and not so good. It said good and poor 3D ISIS. Actually, they're both acceptable. If the person moves a lot, the result could be unusable. But with just a tiny bit of movement, we do see some effect. So in this case, there is a huge lipid signal, which if you don't do any suppression, this lipid signal will be much larger than any of these peaks. And it's based around here. It's just that peak will be huge if you don't do anything to isolate the signal inside the brain versus outside the brain. So in this case, we selected a volume in the back of the head, and we want to eliminate the signal from the fat that comes from the scalp. Here is an acquisition done in the same person. In one of these, the person was holding pretty still. Another one, they moved a little bit during the 8-cycle ISIS. And at the bottom, there's very little lipid signal left. At the top, there is some lipid signal left. We can still quantify the peaks of interest, but this illustrates what happens when someone moves. If someone moves a lot, this peak will become very big, and it becomes difficult to quantify the peaks. Now, I just mentioned a moment ago that there do exist single shot or single acquisition localization methods. So whereas ISIS has a disadvantage that you need to acquire 8 separate acquisitions and combine them, steam, press, and semi-laser are all methods to get localization in a single uh, acquisition. We'll talk first about steam. So STEAM stands for Stimulated Echo Acquisition Mode, and it consists of a combination of 3 90-degree pulses. This is nice, partly because we can have shape pulses that give us 90-degree tips with high frequency selection. You have combinations of pulses, like a spin echo is combining pulses that will give you an echo. When you have combinations of pulses, you can form echoes. And anytime you have 3 pulses, you can make each of them shaped, apply a gradient so that each of them can be made to select a slice in a particular direction, and that means could be X, Y, and Z, or Y, Z, and X, whatever order works the best for a particular situation. But you can apply these 3 as shape pulses with a gradient and get 3D spatial selection. To put that in practice, it's just a little more complicated than I talked about a moment ago. Here are the slice selection gradients. Slice for say X, slice for Y, and a slice for Z, each with a frequency selected shape pulse. There's the one complication here is, see this thing? Just like was the case for the imaging, when we do a slice selection for an image, we have to put a refocusing lobe on the gradient, because here the magnetization is tipped into the XY plane, but only after that can we turn off the slice selection gradient. So once it's tipped into the XY plane, that coherent magnetization sees tremendous inhomogeneity across the sample due to continuation of the slice selection gradient. It dephases the magnetization. So we apply the refocusing lobe. Here we have a refocusing lobe, and note that here we've put it before the slice, and here before the slice. That you can do that. There are also crushers here, and the point of the crushers is to wipe out a signal that came from outside the slice, and also to get rid of something called um, so some additional echoes that you don't want, echoes other than the stimulated echo. But the main point is we have three slices, we have three frequency selected pulses, three slice selection gradients, and then the echo. Here's a kinetic representation of it. First, we tip into the XY plane. Then the magnetization begins to dephase, um, and we apply a slice in another direction, a pulse in another direction, 90 degrees. And now that whatever's in component is oriented along the XY plane also dephases. And now here, after the third pulse, we get some refocusing. All right, I'm going to pause it at different points now. So there, this is just like a pulse acquire experiment at first. Now there's dephasing that occurs, and we apply another 90-degree pulse. So see, that's dephased, or the magnetization is, all of it's being rotated, even though it's dephased. And we have basically a disk of magnetization. Now we have another time delay, and the components of the magnetization that can be projected onto the XY plane, those are spreading themselves out. They are dephasing. So now we have two cones, one up, one down. We have the third 90-degree pulse, which moved everything back into the XY plane as much as it could be. It can't be total because we have the remnants of this previous dephasing. And in our final time delay, we let things refocus, just as we did for a spin echo. But note that they're not going to refocus entirely into a single yellow arrow, yellow vector. There they stop. We have net magnetization in the XY plane. We will detect what's projected onto the XY plane. But because there is the remnants of this previous dephasing, we only observe 50% of the magnetization we would have gotten, say, with a spin echo. But the fact that we can do 3D localization, and that the localization can be done with very sharp volume, sharp distinction on the voxels, often it's worth the sacrifice of 50%. So ISIS will give you more signal total, but you're vulnerable to motion. A spin echo would give you more signal total, but there are only two pulses, so you could only do 2D localization with a spin echo all by itself. And so this is very good for many applications, but do keep in mind that you lose half the signal, so it's good sometimes to explore other options. Now, another approach that's been in use for many years is PRESS, point resolved selective spectroscopy. You have a 90, a 180, and a 180. 3 pulses. They can each be accompanied by 3 gradients for slice selection, and therefore you have an opportunity for 3D localization. Note that this 90-degree pulse has a slice refocusing lobe. These don't have refocusing lobes. They don't need them because they're 180-degree pulses. We turn on the gradient, we run the pulse, and then we turn off the gradient. As long as this gradient is placed symmetrically with the 180-degree pulse, any additional time at the beginning that would cause dephasing is balanced by additional time at the end that would cause rephasing. We also have crusher gradients here to eliminate magnetization that imperfections in the system or stimulated echoes might be generated. And the press delivers as much signal as you would predict for a spin echo with the same length. So that sounds like you should always use press instead of steam. However, these pulses can take longer to play out, so the echo times, the total echo time is often longer than it is for steam. And the 180-degree pulses are generally not as spatially selective as the 90-degree pulses for steam. So if you are acquiring a volume data from a volume that is near a troublesome area, an area with poor B1, B0 inhomogeneity, like the proximity to the sinuses. Um, or maybe you're near an area where you can't tolerate even a little contamination, like from the scalp. You may be better off using steam than press. If you are in a more homogeneous location and you can tolerate a little bit longer echo time for whatever you need to acquire, press is a great choice. So which sequence we use depends generally on a series of what compromises we are going to make. Depends on volume selection, echo time, which molecules you want to look at. You have to evaluate each situation. Then there's semi-laser. So there is a sequence called laser. What gets applied in vivo is semi-laser. So the laser sequence consists of a series of adiabatic pulses. There's an adiabatic 90. We have pairs of 180-degree pulses. And this sequence works well in the presence of, especially in the presence of B1 inhomogeneities, because we're using adiabatic pulses. Say if you had a surface coil, this could be a very good choice because you would get homogeneous 90 degrees and 180 degree tips throughout a large volume near the surface coil. The 180 degree pulses are in pairs, and that's because the tips can generate phase distortions with the 180 degree pulses, and when you put them in pairs, each pair, one pulse compensates the other in each pair. And now there are 6 pulses, so we can apply 6 slice selection gradients. Now this is one of the things you may remember about adiabatic pulses is that they often take more power than the non-adiabatic pulses. When you're dealing with a biological system, like a person, we have to be very careful with the SAR. In another lecture, that was defined as the specific absorption rate. So we don't want to put too much power into the system. And our systems have hardware checks, software checks, multiple levels of security to make sure that power level is not exceeded. But it makes it challenging to apply in humans. And also with all these pulses, now we have a very long echo time, and it can be challenging to look at some systems, like strongly coupled systems like glutamate or glutamine. So semi-laser is what actually it's becoming much more common. The 90 degree pulse, the excitation pulse, is no longer adiabatic. But it's shaped, so it's slice selective. So here's slice selection with a slice refocusing lobe. That gives us one dimension. And now the adiabatic 180 degree pulses take care of the other 2 dimensions. They're still in pairs, so we still have 4 pulses. And so we still have to watch the power, but it's much easier to apply this in vivo. So we have, again, X, Y, and Z. They don't have to be done in this order. There could be reasons that you might find better selectivity. For example, you might find you could want to apply the slice selection of 90 in the Y direction, and then do X for the first pair of 180s. You can choose which order you want to have these in. In principle, any order will work. And this, as I said, it's increasingly being used now, including on clinical scanners. It works very well for many metabolites, glutamine included, if you can keep the echo time short enough. So we have here 4 different ways to achieve 3D localization. ISIS yields full sensitivity, but it requires 8 acquisitions. On the other hand, it gives very, very sharp localization. Steam, press, and semi-laser give you one-shot localization. Steam can get you to very short echo times with very sharp volume selection, but you lose half of your signal amplitude. Press retains all of the signal amplitude, but you have to go to somewhat longer echo times, and it's using 180-degree pulses in addition to the slice selection. So to the excitation pulse. Um, those are not as volume selective, and you end up with a little more outer volume contamination with press. Semi-laser gives you good volume selection. It's 1D localization, but it takes more power, a lot more power than the other ones, so you have to watch the power deposition. And the echo times tend to be a bit longer, but the way the sequence plays out, the coupling is not as doesn't knock down your signal as quickly. So each has advantages and disadvantages. They're good for different purposes. You know, I want to come back to ISIS just for a second. ISIS often gets used actually with phosphorus, with carbon-13. It's compatible with many different sequences. You can use ISIS with a pulse acquire experiment if you want. You can also use ISIS with steam, press, or if you have enough power available, semi-laser, because you can, I know these will give you one-shot localization, but if it's still not isolating your signal well enough, you can combine all of these, any of them, with ISIS. So ISIS can be tacked onto the front of whatever acquisition you want to do to achieve your localization. All right, we move now to water suppression. One of the earliest approaches to water suppression is with binomial pulses. And there are variants on this that go on beyond binomial, various combinations of hard pulses. These were first used even before gradients were in use on the scanners. The idea is to have, say, in the simplest version, it's called a 1-1 bar pulse. The bar means the phase is opposite. This pulse is opposite to that pulse. So we'll say we have creatine as a red vector and water as a yellow vector. We apply a hard 45-degree pulse, and that moves us to this middle frame. The water and the creatine, because the hard pulse is not very frequency selective, the water and the creatine both tip 45 degrees. But we can only be in rotating frame for one thing at a time. Let's say we stay in the rotating frame for water. If we stay in the rotating frame for water and we wait just the right length of time based on the frequency difference between water and creatine, the creatine will precess 180 degrees out of phase with the water. And then we apply a pulse of equal amplitude and duration, minus 45 degrees, so opposite phase. Because the water stayed here, aligned with that initial where we initially put it, it rotates back up to the z-axis. The creatine moved 180 degrees because we had a time delay for the frequency difference to move to allow it to precess. And now that minus 45 degree tip puts it into the XY plane. So for this very simple suppression, we have water moved into the z-axis where we can't see it, and creatine moved into the XY plane where we can see it. Here's a movie of it. We have both vectors going together. Now during the time delay, the water stays put, and we rotate minus 45 degrees. There they go. So again, I'll show it one more time. They move, okay. Creatine's precessing, and now they move back. In this case, a 1-1 bar pulse has a frequency profile that looks like this. If we suppress water, we will choose an optimum for a particular metabolite. But the metabolites actually cover a span of frequencies. So depending on what the frequency difference is with water, they may not, if they don't rotate 180 degrees, like here would be the optimal, whatever metabolites here rotated 180 degrees relative to water, and we get full tip into the XY plane, but if something rotated a little less or a little more, then it would not be. And actually, if something rotates is far enough away, it will precess 360 degrees, match itself with water, and be tipped up into the z-axis, so we see nothing. So the binomial pulse has a pretty severe frequency profile. It was very useful at the time, and to overcome this, there are other arrangements of pulses that Hobie Hetherington and other people have created to get much flatter profiles. Here's an example of what that consequence would be. If we have the ideal water suppression, if we could just make the water mostly go away, this might be the true metabolite spectrum. But with the binomial pulse optimized, for example, for NAA, we have pushed down the creatine and choline resonances. If we could detect them reliably, that's okay. We have to calibrate how big they are, how much they've been reduced by this profile, so that we can do proper quantification. But it's never ideal to reduce signals that you want to measure. Another difficulty, which actually affects many different water suppression methods in different ways, is the shimming. Now, note that the binomial pulse performance depends on frequency. Shimming is designed to make the B0 homogeneity very clean. When the shimming is poor, the B0 is spread out. When B0 is spread out, that means the frequencies are spread out. So if a water peak is broad, then components of it are going to be unsuppressed by the binomial pulse. So at the top we have a well-shimmed sample. At the bottom it's poorly shimmed. Note that the metabolite signals are wider than they are at the top. And here we have residual water spreading through the metabolite region. This is actually a pretty nice problem. I mean, this, as far as water problems go, this one is not too bad because there's a very clear baseline. If the water signal comes through irregularly, it can be difficult to know what is metabolite and what is water. So shimming is always important for spectroscopy. But here is one of the reasons that it can affect the residual, it can affect the water suppression. Another approach is called water gate. So here is just a spin echo, but altered for this for water suppression. So we have here a 90-degree pulse, slice selective. There's our slice refocusing lobe, and we apply it to creatine and to water. We apply it to all across the spectrum. So everything at the beginning is tipped into the XY plane, and it's coherent. Now we apply a crusher gradient. So it's as if we are temporarily creating a bad shim. We're making a big T2 star effect, and we get dephasing. So the creatine and the water, they both dephase because of this crusher gradient, plus whatever B0 inhomogeneity exists here. We have a 180-degree pulse, and note that it doesn't look like the other 180-degree pulses that have been drawn in the schematics. This could be a shaped pulse, it could be a combination of hard pulses like binomial pulses, but it's designed so that it will apply a 180-degree pulse only to creatine. So the creatine is flipped 180 degrees. The water is not. Then we apply another crusher gradient, identical to the first one. And then after this, the second half of an echo time, we want this echo delay to match this echo delay. That means that we have a spin echo. But we only have a spin echo for magnetization that has seen the 180-degree pulse. So creatine sees the spin echo and it refocuses. Water did not see the spin echo, did not see the 180-degree pulse, and it continues to spread out under the influence of this crusher. So for creatine, we tip into the XY plane, then we flip 180 degrees, and then we rephase, and there's a creatine signal. For water, we tip into the XY plane, we dephase, and nothing happens. and we dephase some more, and the magnetization is wiped out. There's no signal. Another approach that is not dealing with another approach that's not based on an avoidance of excitation of water is T1 relaxation. This is analogous to T1 weighting of an image, where you select a particular time you do an inversion pulse, and you wait a particular time based on how long some tissue, like CSF, takes to relax, and do your acquisition. And if you can time it so that for the imaging, if you time it so that the CSF Z magnetization is going through 0, then when you take your image, the CSF will be dark in the image. In this case, we could apply a 180-degree pulse limited to, say, frequency selective around water. So now we're not using the frequency selection for spatial localization. We're using it for frequency, for spectral localization. We select a band around water, flip 180 degrees, and we wait the right length of time based on the water T1 for the water to have reached 0 Z magnetization. And then we do press or steam or semi-laser. We do some kind of acquisition for localization, or we do a pulse acquire if we don't need the localization, and we don't see the water. Now, if you waited a very long time, then it would be as if you didn't do anything. If you waited a very short time, you would have a big negative water peak. But if you wait just the right time, the water is mostly nulled. So in this example, we have a water inversion pulse. We wait some length of time, and now we start a general slice selective 90, maybe a slice selective 180 if we're doing a two-dimensional spin echo approach. It should have very little water in it. So here you can use a hyperbolic secant, for example, to invert just the water and leave that affects the Z magnetization of the water. So these sit unaffected. They're sitting as if they're just at rest. You haven't done anything to them. The water gets inverted. Then we wait a period of time appropriate for the water to reach a null, and now we start the experiment we wanted to do, like a spin echo or a press. And we can see these without interference from that. Much more common, actually, is chess. That has become very common now. Chemical shift selective suppression. It can be used for, the same approach can be used for outer volume suppression. That's another aspect we talk about in the course. But the idea is to select either a location in the brain, maybe, or in this case, a region of the spectrum. We apply a frequency selective 90-degree pulse, and then we wipe out the magnetization. So at this point, there's no XY magnetization, there's no Z magnetization but just for water, because we selected right around water. The metabolites, because we made the 90-degree pulse frequency selective, the metabolites are unaffected. They continue with just Z magnetization. And then here is where you begin your spin echo, your press, whatever excitation you want to start. One of the challenges with chess is that it relies on an accurate 90-degree pulse. If you tip 45 degrees, you can suppress whatever component moved into the XY plane, but you're still going to be left with a lot of Z magnetization in water. You have to tip into the XY plane. You need a 90-degree pulse to get the chess to work right. Vapor is another method from Koch, 1999. This method he developed to overcome B1 inhomogeneity. Say, no coil is perfect. Surface coils have a more dramatic problem with B1, but this can have advantages even for volume coils. It's a series of pulses applied with specially set timings, and the pulse amplitudes are set relative to one another. The timings are based on the T1 relaxation of the material you're trying to um, to suppress, say, water in gray and white matter. Um, and so if you want to run this in a tissue that has different T1s or different magnets, you're going to have to adjust the time delays between the pulses to whatever value is appropriate for the T1 in whatever system you're working on, whatever material you're using. But the idea is that whether you have say, if the ideal pulse is 95 degrees here, but some of the region sees 125 degrees or 65 degrees, and if you follow this recipe across here, apply these different pulses, they're all going to end up zeroing out your Z magnetization. And then at this point, you can run the press or pulse acquire or whatever you're trying to run. Um, so this is also a preparatory water suppression method. This happens before your main sequence. And the water suppression is often a combination of methods. Just like we talked about the volume suppression being, you could maybe combine ISIS with steam. You can also apply various methods together. So, for example, you might use vapor followed by a binomial excitation pulse. And if the binomial excitation pulse eliminates 98% of your magnetization, and vapor eliminates 99% of your magnetization, then what you're left with is 1% times 2%, which is a very, very small fraction. So, and what happens when we're developing pulse sequences, we just test to see we'll test what we think will work. We'll develop a steam sequence, and we know that steam by itself is not going to suppress water. So we're working at this point with a bottle of water that contains maybe GABA and creatine and NAA. We'll stick a unit of chess in the front and say, oh, that looks nice in the bottle of water. And then a volunteer will come and we'll put the person in and test it. And the water suppression is not very good. So we'll add another module of chess. And maybe that works fine for that person. But we try a few more people and we find it's not really reliable. The spectra there's not enough water suppression. So maybe we'll add an inversion recovery sequence ahead of that. Well, we may also find that the steam localization, even though it's good, it's still not enough. So we can pile in some ISIS. Now there's a limit of how much of this we can do, and some of these interfere with one another. Like we have to be careful with the inversion recovery and the ISIS because they're both inversion related. They can interfere with one another. If we put a whole lot of, if we suppose, if each chess module were to suppress 99% of the water, that sounds like you should just put a string of chess pulses in. At some point there's a limit because between each chess pulse, each chess module, there's some T1 relaxation. And if you put a whole lot of these together, there's going to be a little bit of Z magnetization for the water that recovers each time. So there's a minimum, at some point there's diminishing returns. Or if you've applied something in advance, by waiting too long here before you do your actual acquisition, you can spoil some of your localization methods. So they have to be done judiciously, but they are very often done in combinations. To summarize for today, the pulse acquire and spin echo measurements they're the simplest NMR pulse sequences, and they form the basis for most measurements performed in vivo. But we didn't talk much about those today because we looked into other aspects. We need more than that typically when we're working in vivo, especially for proton spectroscopy. So water suppression, something you don't typically do for imaging because you usually want to see the water, but for spectroscopy, very necessary. Water suppression forms a crucial part of proton spectroscopy studies. And there are a variety of techniques that we can apply together in combination to achieve it. Notice this specifies proton MRS studies. If we were doing nitrogen, carbon-13, phosphorus, those don't have they don't have any hydrogen in them. I mean, there could be hydrogen in the molecules, but there's no way that we can detect hydrogen when we're in the frequency band looking at phosphorus. So water doesn't interfere with our signal. For proton spectroscopy, the water is very, very present. The three main methods of localization in use today for proton spectroscopy are steam, press, and semi-laser. We do use ISIS. It's still used for some applications, but on a clinical system, you won't often encounter it. And the reason people generally don't like ISIS is that it requires 2 to the n measurements, where n is the number of dimensions that you want to localize. So for 3D localization, it takes 8 blocks of 8 scans to get a reliable localization. And what really favors it is that it can be used well with to localize carbon-13, phosphorus. It can give you very sharp localization, very well-defined voxels. Steam, press, and semi-laser, those can achieve spatial localization each in every time you apply them, each measurement. You don't need blocks of 8. We do almost always need to signal average. So you may need 64 or 128 or 256, 300 scans, but each one of those should be sufficient to localize your 3D volume by itself. So steam, press, and semi-laser, each of them has their own advantages. Steam gives you pretty sharp localization, but it eliminates half your signal. You can also go to very short echo times with steam. Press, you need to go to longer echo times, and the volume selection is not as sharp, but you do get full amplitude. So it depends where you're looking and what you're trying to see. And semi-laser gives you good volume localization, but it requires more power deposition. So you have to think about how quickly you need to acquire, what metabolites you want to see. Everything depends on the context of what your measurement is. That concludes today's lecture on basic NMR spectroscopic sequences.